Welcome to the next learning unit in the chapter on PV system components. In this learning unit, we will deal with the different cables in a PV system. The direct current generated by solar modules should, if possible, reach the inverter without losses and from there to the consumer or to the grid connection point. This is a function of the different cables in a PV system. Unfortunately, this transport is not completely loss-free, since every cable has a resistance at room temperature. This resistance causes a voltage drop in the cable and a loss of power. In this learning unit, we will look at how these losses can be minimized. First of all, let's see where in the PV system we find which cables. Let's start with the PV modules. The modules of a system are interconnected to form one or several strings. The connection cables for this purpose are already pre-assembled on the back of the modules and only have to be plugged together. From here, the string currents are carried on via the string cable. Since the string cables partly are in an outdoor location, they must be able to withstand extreme weather conditions. Therefore, protection against moisture and UV play a major role. In addition, the cables at this point in the systems carry a direct current, so they must be double insulated and only carry one wire. In some systems, there is a junction box in which the strings are connected in parallel. The current is then routed from the generator connection box to the inverter in the DC main cable. This cable is also a direct current cable and must be double insulated accordingly. If several strings are interconnected, the main DC cable carries higher currents than string cables and is therefore often significantly thicker. Behind the inverter, the lines no longer carry direct current but alternating current. From here, the electricity is transported to the grid connection point. Cable losses occur in all the line sections listed here. But how can we calculate these losses? The losses in a conductor depend mainly on its ohmic resistance. The ohmic resistance depends on the length and the cross-sectional area of the conductor. In addition, the material properties also have a major influence. In general, the ohmic resistance can be determined from the specific resistance ρ times cable length divided by the cross-sectional area of the cable. The resistivity is a temperature-dependent material constant. It is often expressed in ohms times millimeter square per meter. It can also be expressed by the reciprocal of the conductivity kappa. In addition to kappa, the Greek letters sigma or gamma are also commonly used as symbols for the electrical conductivity. From the equation we can see the following relationships. The greater the conductivity, the lower the resistance of the cable. In addition, the longer a cable and the smaller its cross-section, the greater the resistance. For a small resistance, a cable should therefore be as short and thick as possible. It is important to mention here that the temperature also has an influence on the resistance of the cable. At higher temperature, the resistance increases. With poor rear ventilation, the module backsides can heat up to around 70 degrees Celsius during operation. The ohmic resistance of kappa for any given temperature can be calculated using the equation shown here. Here alpha is a material-specific temperature coefficient and is 0.39% per Kelvin for kappa. As an example, let's look at a 1 meter long cable with a cross-section of 1 square millimeter. Copper has a conductivity of 56 ohm meter per square millimeter at 20 degrees Celsius. The resistance of the cable is therefore 56 ohm. If we insert these values into the equation and calculate the resistance of copper at 70 degrees Celsius, we get a value of 66.9 ohms. That is an increase of almost 20%. Of course, assuming a temperature of 70 degrees Celsius is an extreme value. The major part of the cable is not on the back of a module and will not reach this temperature. Especially for the main DC cable, which does not run on the roof, room temperature may be assumed for the following considerations. We can now calculate the resistance of the cables in our PV system. The resistance causes a voltage drop between the PV generator and the load. Let's have a look at the DC cables and consider a simplified system in which only one module is connected to a consumer. We represent the resistance of the cables by R cables. Since both positive and negative terminals of the module are connected to the load, the cable resistance also appears twice in the circuit diagram. Let us now calculate the losses in the cable at room temperature. According to Ohm's law, we can calculate the voltage drop in the cables from the product of the current and the cable resistance. Finally, the absolute power losses in the cables are given by the product of the current and the voltage drop. The power losses are therefore directly proportional to the resistance of the cables multiplied with the current squared. In order to reduce the power losses in the cables, the resistance of the cables should be as low as possible. To achieve this, a material with the highest possible conductivity can be selected. For solar systems, copper and aluminium cables are mainly used. Copper, with 56 ohms meters per square millimeter, has a much higher conductivity than aluminum, which has a conductivity of 34 ohms times meters per square millimeter. However, copper is also somewhat more expensive than aluminum. Silver would have an even higher conductivity, but silver is almost 100 times more expensive than copper. For these reasons, in most PV systems, copper cables are used. The next way to reduce resistance is to make the cables as short as possible. However, it is often only possible to shorten the cable length to a certain extent, for example because the cable have to connect the modules on the roof with the inverter in the basement, which means a certain distance. Lastly, resistance can also be reduced by choosing a cable with as large a cross-section as possible. Of course, you should always choose a very large cross-section, but this would also increase the cost of the cables. Therefore, in practice, the cross-section is chosen just large enough so that the power losses in the cables do not exceed 1% of the generator peak power. If we insert the equation for the cable losses as well as the total power P equals I times V, we get the following condition. The requirements for the cable cross-section increase proportionally to the current and the cable length, but decrease with increasing voltage. In practice, however, only certain cable cross-sections are available. Therefore, it is usually rounded up to the next larger common cable cross-section. Common cross-sections for solar cables are 25, 16, 10, 6 or 4 square millimeter. We have just seen that the required cable cross-section depends not only on the length of the cable, but also on the current to be transported. It is also inversely proportional to the voltage. Let's take a look at what this means for the various cable sections in a PV system. In string cables, a certain number of modules are connected in series at a time. The current in the string cables therefore corresponds to the current of one module. For the cable dimensioning, we use the module current in the MPP. The voltage is equal to the number of modules per string times the MPP voltage of one module. However, if several strings are connected together in parallel, the main DC cable must be considered separately. The current now corresponds to the MPP current of a module times the number of strings connected in parallel. The voltage corresponds to the voltage in the string cables. In the example shown here, we have 3 strings connected in parallel. compared to the string cable, the required cable's cross-section is therefore tripled. As mentioned above, the cable cross-section is usually rounded up to the next larger common cable cross-section. In addition to the DC cables between the modules and the inverter, it is of course also important to look at the AC cables through which the inverter feeds the electricity generated into the public grid. To understand what to look for in AC cable, let's first take a closer look at the three-phase system used in most countries. In such a system, the voltage is divided among three separate lines. The three voltages are shifted in phase by 120 degrees to each other. They therefore reach their amplitude with a time lag. The effective or average value of the three voltages in Europe is 230 volt, each with respect to the ground potential. The three lines are often simply referred to as phases. In addition, a further line is usually included in the three-phase system, the so-called neutral conductor. The neutral conductor is connected to the neutral point of the low-voltage transformers, that is, to the point where the three phases are brought together. In the three-phase system, the currents flowing through the three phases lines add up to zero at any moment. Therefore, the neutral conductor carries no or very little current when the three phases are symmetrically loaded. Thus, if we feed the same amount of current into all three phases with a three-phase inverter, the neutral conductor remains unloaded. The situation is different if only one phase is used, as in the case of an ordinary single-phase consumer or an inverter feeding in a single phase. In this case, the circuit used runs via a phase line and the neutral line. When alternating current is transmitted over a power line, there is a voltage drop across the line that we can calculate, just as in the case of direct current. Let's look at the single-phase inverter first. Here the circuit runs over a phase line and the neutral line. This looks very similar to the DC side. Therefore, the voltage drop can be calculated by 2 times R times I, just like on the DC side. Since we are dealing with an alternating current, however, we have to consider a special thing here. In addition to pure active current, which we know from the direct current, so-called reactive current also occurs here. Only the active current leads to a voltage drop across an ohmic resistor. The ratio of the active current to the total current is described by the so-called power factor, cosine phi. A power factor of 1 corresponds to pure active current, while a power factor of 0 corresponds to pure reactive current. In a modern inverter, the power factor is usually between 0.8 and 1. We will deal with the power factor and the meaning of active and reactive current in more detail later. Since only the active current component is important for the voltage drop on the AC side, we multiply here with cosine phi. In the three-phase inverter, the current now takes a slightly different path. As we have just seen, the current only runs through the three phase lines, while the neutral conductor does not carry any current. So we have 3 lines, but each of them is loaded with only 1/3 of the current. The factor 2 is therefore omitted in the equation for the voltage drop. Instead, however, the factor root square of 3 appears. Let's look at where this factor comes from. Here you see a vector diagram of the 3 conductors' voltages in the three-phase system. In the middle, at a potential of 0, is the neutral conductor. Seen from the neutral conductor, all 3 conductors carry the same voltage, but with a phase shift of 120 degrees to each other. In the European area, the voltage between the neutral conductor and the phase conductor is 230 volt each. However, the voltage between the neutral conductor and the phase conductor is not the only voltage we can use in this system. We can also use the voltage between 2 phase lines. In the vector diagram, this voltage corresponds to the connection between 2 of the voltage vectors, for example, between V2 and V3. We can already see in the diagram that this voltage is much larger than, for example, the voltage V1, V2 or V3. Let's try to calculate the magnitude of the voltage V23. For this, we consider the triangle between the 0 point, V2 and V3. This triangle is an isosceles or equal-sided triangle. Since the sum of the three interior angles in a triangle is always 180 degrees, the angle alpha must be 30 degrees. In this triangle, we now draw the height and look at the triangle marked in green. It is a right triangle. The adjacent of alpha corresponds exactly to the half voltage between V2 and V3. And accordingly, we can calculate V23 via the cosine of alpha. V23 is therefore cosine of 30 degrees. Cosine of 30 degrees in turn corresponds exactly to square root of 3 divided by 2. Thus the following applies. The voltage V23 is equal to V2 times the square root of 3. For a mains voltage of 230 volt, this corresponds to a voltage of 400 volt between two phase conductors. The same consideration apply to the voltage drops in the line. This results in the factor of square root 3 in the calculation of the voltage drop. Now we know how to calculate the voltage drop in the single phase and the three-phase system and can use this knowledge to dimension the cables. Basically, we proceed in the same way as on the DC side. However, unlike the DC side, where the voltage drop should be no more than 1%, on the AC side 3% are tolerated. We can now insert the equations we have worked out for the AC side voltage drop into the equation for the cable resistance, R cable, equal to cable length through specific resistance through cross section, thus resulting in the conditions shown here for the cable cross sections in the AC circuit. In the equation, Vn corresponds to the main voltage of 230 volt. Mainly because of the higher tolerance of the 3% voltage drop, significantly smaller cross sections are used on the AC side than on the DC side. Let's summarize this unit. We have learned that every cable has a certain ohmic resistance, which is greater the longer and the thinner the cable is. The resistance causes a voltage drop in the cable, which depends on the resistance of the cable and the current. The cables for PV systems are designed so that the losses on the DC side are less than 1% and on the AC side less than 3% of the transported power. Since the cable lengths can usually be shortened only to a limited extent, the minimum size for the cable cross-section is usually calculated. The cable cross-section increases proportionally to the current and the cable length, but decreases with the increasing voltage. Thank you for your attention.